Morning to all of you. In today's demonstration, I would like to deal with certain examples involving a batch reactor model in Aspen. In fact, at the end of this session, you should be in a position to solve any problem involving a batch reactor, however complex the kinetics may be. To start with, consider a liquid phase reversible reaction because it is given as elementary, so this reaction is second order in both directions. You have been given the forward rate constant and also the backward rate constant, and you are required to use a batch reactor model in Aspen to calculate the time required to obtain 30% conversion when you are operating the batch reactor at isothermal conditions, in isothermal conditions at 100 degrees centigrade. The initial charge into the reactor along with its composition, temperature and pressure are also given to you. So let us look at how to solve this problem using Aspen simulation. For example, we already know what are the components involved in this problem: acetic acid, ethanol, ethyl acetate and water. So the first step in any process simulation is to define these components. So let me first try to define these components. Acetic acid, so let me call it as maybe AA. Ethanol, and ethyl acetate. So let me call it as EA, and of course water. Selected the components. Now you are required to identify that you go to next step and you are required to identify an appropriate property model. Probably I will be selecting an NRTL model to represent the properties required for this system. So after selecting the model, you can go to the next input screen. Okay. These are the properties that are available, the various parameters that are available for these components that we are going to use in the case of NRTL method. Now I am going to simulation environment, wherein you will be in a position to draw the necessary flow sheet. In fact, we are only trying to use a batch reactor. So let us deal with a batch reactor example. Now, having selected this model, now I am required to add input and output conditions. You can see batch reactor charge is required. So I am adding one input, similarly an output. So that's all as far as this model is concerned. Now let us look at what is the next information that may be required. So you were given already that this system is entering at 100 degrees centigrade, 100 degrees centigrade and 1 bar, 1045 kg. So this is the composition: 13 mole percent acetic acid, 35 mole percent ethanol and 52 mole percent water. So let me enter this information. 100 degrees centigrade and 1 bar. So we were given with mass, so it is 1045, and you know the composition of this system in moles, mole fractions. Choose mole fraction. Acetic acid is 13%, ethanol is 45%. Water is 52%. You can see this stream has been addressed. So we may have to provide some information with respect to the block. Let us go to the next input screen. So now this is with respect to the batch reactor. We are already specified that it is operating at a constant temperature of 100 degrees centigrade. And when we say pressure is equal to 0, we are assuming that there is no pressure drop across the reactor. And this reaction is undergoing in liquid phase. So let us go to the next. Now we have not specified any reaction, so press new. So let us say by default it names it as R1, and I am selecting a general model to represent the kinetics for this reaction. So we will define the kinetics and other information slightly later. So let us go ahead. So criterion, where do you want to stop, right? So I wanted to obtain a conversion of 30% in the reactor. So stop value is 0.3. Component is maybe acetic acid. I think it is the limiting reactant. So we have addressed this stop criteria. Let us say operation times. So you were given with some idea. Even if you don't have an idea, you can assume some value. And I would like to have quite a number of profile points. It's up to you. You can randomly choose this number. And what is the increment, time interval between profile points. So we have addressed all this information. Of course, some information with respect to the kinetics need also to be provided. So let us go to the next input screen. So this is new. So you can say maybe forward reaction. Name of this reaction. We know what is the forward reaction. Acetic acid coefficient is 1, stoichiometric coefficient. Reacting with ethanol, again the stoichiometric coefficient is 1. And the product of ethyl acetate coefficient is 1. And water, again the coefficient is 1. Next. Right? Now you press next. Now you are given with the kinetic information. In the forward direction, the rate constant is 8 into 10 power minus 6 cubic meters per kilomole second. Remember, the rate constant must always be given in SI units. Depending on the order of the reaction, the units may change, but all of them should be in SI. So 8 into 10 power minus 6. I'll provide that information here. 8e minus 6. So again, be careful that the reacting phase should be liquid. Already in the reactor, we said it is a liquid phase reaction. And because the reactor is operating at isothermal conditions, we may not require the information about the activation energy. So you can say 0. Only when you want to calculate the value of rate constant at different temperatures, you may require the value of E. Otherwise, it can be specified as 0. Whatever value that you give here is not going to affect your results. And we also know in the forward direction, the concentration, it is a second order reaction. So the exponent with respect to concentration of acetic acid is 1 and also ethanol is 1. So we have specified this. You can see kilomoles per cubic meter second. These are the reaction rate units, right? Accordingly, the rate constant must also correspond to the same SI units of system. Now we have defined this. Let me go back once again because there is another reaction involved with this reaction 1. So I will write the second reaction. This is the backward reaction. Now you know the same components. Ethyl acetate, the coefficient is 1. Now we are talking about the reverse direction of this reaction. 1. And it is going to give you acetic acid and ethanol. Again, in the same way, we need to define the kinetics for this backward reaction. We have already defined this with respect to the forward reaction. Now I'll select the second backward reaction. And this rate constant is given as 2.7 into 10 power minus 6. So again, as I said, the value of E is not required because we are operating the reactor at isothermal conditions. The value of rate constant is already available at a temperature of 100 degrees centigrade. Once again, in the reverse direction, it is first order with respect to ethyl acetate and also first order with respect to water. So we have completed all the required input required for specifying this problem. So we should be in a position to go ahead with our simulation. I think there is a problem with my input. Stream 1, let me check it up. 10%, 35 mole percent. I'm sorry about this. Now the total of mole fractions must be equal to 1. So let me reset the simulation and run it again. Now we have simulated the problem. So you should be in a position to look at the results. You can see from this mole flows, acetic acid about 4.8 kilomoles per hour of acetic acid is entering. Out of this, 30% is converted, should be converted, and we need to have 70% of whatever acetic acid that may be entering should be there in the exit. You can check it up. 4.08 into 70% is 2.8558. Now, how much time was required to achieve this 60% conversion? Of course, you can also look at the remaining results. I'll look at the block results. Now, of conversion, we require about 1.79 hours. If you want, you can convert that into either minutes. About 107 minutes are required to achieve this conversion. So in this fashion, you already know, if you want to solve this reversible second order reaction analytically, this may be slightly complex because you need to derive the relation between time versus conversion for a second order reaction. If you are interested, you can also check up this answer with your analytical result. Now, I would like to deal with maybe another example just to give you an idea about the complete batch reactor. Consider a first order irreversible reaction. So you have cis-butene is being converted into trans-butene. The rate constant is given in SI units. This is the rate constant. So 1 kilomole per hour of cis-2-butene is charged at 25 degrees centigrade on 1 bar. Find the time required to reach 90% conversion in a batch reactor operating isothermally at 25 degrees centigrade. Now, in the previous problem, we have dealt with maybe a reversible reaction. Now, I would like to deal with an irreversible reaction. So let us define the components as we have done in the previous case. So this is cis-2-butene and trans-2-butene. We may not be able to define all that trans that we use. So these are the only components that I am using in this problem. So again, choose some property model. You can go into the details of how to select an appropriate property model to simulation environment. Again, use the batch reactor. Connect input and output. Next, specify the required input. Now you know that this is entering at 25 degrees centigrade and 1 bar. 1 kilomole per hour of cis-2-butene is entering. Pure A. 25 degrees centigrade, 1 bar, and 1 kilomole per hour of cis-2-butene is entering. So we have addressed this stream 1 that is entering into the reactor. Now let us go to the other input. Again, the reactor is operating at a constant temperature of 25 degrees centigrade. There is no pressure drop. It is in a liquid phase reaction. So say new R1. I'll select general, or of course you can also select power law model if you are interested, as we are doing with the other examples. Then next, start criteria, again similar to the previous one. So we wanted to achieve a conversion of 90%. Cis-2-butene and below. Next, we may not be knowing the time, so let me presume this is a first order reaction supposed to be fast. Okay, as we did some 5 hours. I don't have any idea about the possible uh, time required for converting the cis to butene with 90% conversion. So we have addressed all these issues. Of course, we need to specify the kinetics. Say new first order reaction. It will take only a maximum of 9 or 8 characters. Cis butene coefficient is 1 and the product is trans butene coefficient is 1. Next. So we have given the stoichiometry. Now we need to provide the necessary kinetic information. So reaction class is power law. K value is given as 0.003833. I will provide this information. So again, because the rate constant is given at a temperature of 25 degrees centigrade, we don't have to worry about this. Uh, this is an elementary chemical reaction, irreversible chemical reaction. So the exponent is 1, first order. So you can see all the required input is complete. So we should be in a position to run the simulation. We got to our result. You can check up the stream summary initially. So 1 kilomole of cis butene is entering. 90% if it is converted, only 10% of 1 should be leaving. So 0.1 kilomoles per hour is found in the exit, or about 0.9 kilomoles per hour of trans butene is available in its output. How about the time? So you can see, in order to reach this 90% conversion, operating the reactor at 25 degrees centigrade, we require about 0.166 hours of time, about 10 minutes. Of course, in this case, it may be quite easy for you to check up what is the time that may be required in order to solve the problem. You know, it is ln minus ln 1 minus xA is equal to kT. xA is known, K is known. You try to calculate the time analytically and try to compare it with the simulation result. This way, you must be in a position to solve any problem involving a batch reactor, however complex the kinetics may be. So in the same way, let me also deal with one more example to make it